Welcome to Unit 9, Lecture 3, continuing talking about the atmosphere. Now we're going to look at the solar radiation, the waves of light and heat that come from the sun, hit the Earth, and cause the Earth to warm up. Right here in this opening slide is an overall summary of what happens as the sun's rays, the solar radiation, leaves the sun and comes into the Earth. Now obviously it's not drawn to scale, the Earth is not that close to the sun, but it gives you a decent idea. And I know it's a little hard to read, but we're going to hit on most of this stuff on the next few slides anyway. So let's get to it. First off, let's talk a little bit about radiation. People hear radiation and they think of atomic bombs, they think of treatment for illnesses, but really what radiation is, it's just a form of energy. It's how a lot of energy travels around the universe. And in fact, all of the sun's energy that travels to the Earth, or all of the energy that the Earth receives from the sun, travels as radiation. And radiation can be many different forms of energy. All the forms of energy that travel through space as waves are classified as radiation. This includes light, sound, UV radiation, ultraviolet, IR or infrared radiation, X-rays, gamma rays, FM and AM radio waves, and microwaves. And that's just a few of them. Those are like the ones you've probably heard of most, if not all of those. And all of those are forms of radiation. And what we can do is we can look at these forms of radiation and rank them based on wavelength, or how long it is from the start of one wave to the start of the next wave. Also look at them in terms of energy. The longer the wavelength, the less energy. So if we look over here, down here where we have radio and TV waves, these are the longest wavelengths. They have the least amount of energy. Whereas over here, when we get into the gamma rays, they have really short wavelengths, and they have the most energy. So we'll write low energy over here, and high energy over there. And all of these together make up what is known as the electromagnetic spectrum, which is all of the different frequencies or wavelengths of electromagnetic radiation. Right? These all interact with each other. And what we do is we measure the waves from any fixed point to the identical point on the next wave. And that is a wavelength. It's how long it takes to get from one wave to another. Right? And different radiations have different types of wavelengths. And right in here, just this little sliver is what our eyes can pick up. Visible light is right in between infrared, infra meaning below, and ultraviolet, ultra meaning greater than violet. And if you look at it, the lowest color of visible light is red, the highest color is violet. So anything between red and violet we get to see. Anything below red is infrared, and then it eventually moves into the microwaves and radio and TV waves, Anything above violet is the ultraviolet, then the X-rays, and the gamma rays. And some of these we've used for other procedures. Infrared ends up being heat and heat energy. And some animals, like the pit vipers, snakes, they have special sensors that can sense heat energy and helps them find warm-blooded prey. We are not able to see that, but if you have infrared goggles, now you can see heat signatures. And lets you see not only in the visible light, but also in the infrared spectrum, which is a little bit lower. So how does this affect our atmosphere? Well, all this solar radiation comes from the sun, and it hits our atmosphere. And then it begins to scatter or spread apart. And the reason for that is because the atmosphere is not empty. It's full of clouds and dust and water droplets and other molecules, and it disrupts the path of the radiation. Like if I was shining a laser pointer, alright, that laser pointer the path might get disrupted by something. If I'm trying to shine it from my room across the hallway into Mr. Nolan's room, and somebody walks by, well, that person will disrupt that ray for a little bit. And so this causes the light or the sun's waves to move, to scatter. And so it happens whenever particles or other gases reflect or bend the solar rays. Alright? So if somebody put like a glass of water in front of the laser pointer I'm trying to shine into Mr. Nolan's room there, the water will cause the light wave to bend a little bit. That is something called refraction. The bending is called refraction, while reflection is like if a mirror. I mean, you kind of know what that is already. And so this change, whether it bounces back or bends, this change causes the rays to travel out in all directions, but it does not change their wavelengths. So as the scattering happens, that's why we tend to see variations in the colors that we see. Another key point of reflection happens on Earth's surface. That's something known as the albedo effect, and we're going to do a lab on this next week, or later this week, depending on whenever you're watching this video. And albedo is the fraction of solar radiation that is reflected off the surface of an object. This happens on the ground. Some things on the ground reflect more light than others. Some objects reflect more light than other objects. A mirror reflects all light that hits it, whereas some other things don't reflect much light at all. So the energy that gets absorbed or reflected depends on characteristics of the object. All right, specifically color and texture, and we can get into others like composition, volume, mass transparency, state of matter, all that other stuff. Alright, specific heat, a lot of different things. But we're going to focus mainly on color and texture. Alright. High albedo is usually from smooth, light-colored surfaces. So I mean, you know this from summertime. If you have a light-colored concrete sidewalk and then you have blacktop in the street, the pavement in the street, and you let it, it's a nice hot sunny day, and you go out in your bare feet, the sidewalk will not feel as hot as the street, and that's because the sidewalk is actually reflecting more of the energy. It's not absorbing as much like the street is. And low albedo, which is the opposite of high albedo, would be rough, dark surfaces. kind of like that the street, which is a high albedo. It absorbs a lot of radiation. In the lab, we're going to be shining a light on two containers. One is lighter in color and smooth. The other one is really dark in color and not as smooth. And we're going to see which one will heat up more and which one would cool down more. And so this will take a look at the intensity and amount of time it takes for the material to receive radiation. And it looks at how much energy is reflected, how much is absorbed. Big thing though, lots of reflection, high albedo, with smooth and light colored surfaces, whereas a low albedo, a lot of absorption, very little reflection with rough, dark surfaces. Absorption is gathering up the energy. Alright, so solar radiation that doesn't get reflected, doesn't bounce back, it gets absorbed by different surface materials, rock, soil, water. It will heat up the water. That's why in the summertime, when we receive more solar radiation in the northern hemisphere, lakes and ponds and everything heat up. They're heating up because of the sun. The sun is hitting on them and warming them up. Whereas in the wintertime, there's not as much solar radiation hitting us, and so they can't heat up as much. And the absorption of thermal energy by the ground heats up the lower atmosphere where we live, and it keeps Earth's surface much warmer than it would be if there was no atmosphere. Without the land heating up the lower atmosphere, we wouldn't really be able to live. It would be really cold down here. So that absorption of the thermal energy helps all living things survive. Alright, and part of that is something called the greenhouse effect. Now, we hear greenhouse effect, we might instantly think of Al Gore and some global warming, maybe even scientific nonsensy stuff, depending on your views on the matter, and we'll get into those more in the climate change unit. The greenhouse effect is a real thing. It's what keeps the Earth warm. And what happens is we get solar radiation coming in and hitting the Earth. Alright, passes through the atmosphere, warms the Earth's surface. That energy is absorbed by the Earth's surface, and eventually it is radiated or released back into the atmosphere as heat. And some of that heat escapes into space. However, some gases in the atmosphere, such as methane and carbon dioxide and water vapor, reflect or absorb some of that heat and re-radiate it back toward the Earth. And so keeps it in the lower atmosphere. And so that keeps the lower atmosphere a little warmer, and we get the temperatures that we see, which are warmer than they would be if we didn't have this greenhouse effect. So it kind of insulates the Earth, these greenhouse gases, and without them, the Earth would be a much colder place. With too many of them, the Earth would be a much warmer place. And we know that we can test in the lab that carbon dioxide keeps more heat in than regular air. So as there's more carbon dioxide in the air, more heat should be getting trapped. And that's the basis behind the concept known as global warming, even though I think that is a really horrible name for it and has led to more problems than it has solved. And I'll get into that way later. The other thing to look for is the Earth's tilt. All right, because the Earth is tilted at some times of the year, one of the hemispheres is tilted toward the sun. All right, this is kind of like what the Earth looks like right now. The southern hemisphere is getting more sunlight than the northern hemisphere, more radiation, so it's warmer in the southern hemisphere, and right now they're having their summer. In our summer, it's the opposite. The northern hemisphere is tilted, and so we get the after that energy is absorbed re-released into the atmosphere through processes of conduction and convection. Alright, conduction is the direct transfer of energy through a material. So if you turn your stove on and then you put your hand on the burner, you're conducting that heat right into your hand and burning yourself. Alright, that is conduction. So it happens from collisions between particles, warm substance. So conduction only heats the lowest few centimeters of the atmosphere, so you have to have direct contact. So what you really need to think of is you really need to think of that putting your hand on the burner of the stove. Your hand burning, that is conduction. The other way that heat flows is convection. We went over convection in the first marking period, all right? Look at differences in density, where less dense stuff rises, more dense stuff sinks. So hot rises, cool sinks. All right, this happens in gases or liquids. All right, when they are heated unevenly, and this you can see in your bathroom when you take a shower. The steam rises out the top. It's hotter. All right, less dense than the cool air at the bottom. So the warm air is at the top of the bathroom. The cool air is at the bottom of the bathroom. And it's a continuous cycle of warming and cooling, cold air sinking, warm air rising, that heats and warms the earth, and it leads to convection cells in the air, which are similar, because they're the same process as the convection cells that are in the Earth's asthenosphere driving plate tectonics, but this is in the air, and this really causes weather patterns, global weather patterns, global winds, and all that fun stuff that goes with it. So just to end here, answer the question, why do generally do deserts get colder at night than other areas? Well, the thing about deserts is the air in deserts contain little water, and water is an insulator. All right, it takes a lot of energy to heat up water or cool down water. And so water would normally absorb a lot of heat during the day and release it at night. Well, since there's no water, you don't have that balancing factor of the water absorbing a lot of the radiation and then giving it back off, which would keep the daytime temperature lower, let the nighttime temperature be a little bit higher. Also in the desert, if you think of it, sand is not particularly light or dark in color. It's kind of a middle color. It's kind of rough. But there's nothing in the air to hold on to the heat. And so the heat re-radiates away quickly, and there's nothing else to absorb it and kind of keep it there. And that's why deserts are cold at night, and this is all due to the same thing, idea of solar radiation and reflection, conduction, and convection. So that's kind of how the Earth heats up, cools down, how the sun's rays interact with the Earth, and everything. So if you have any questions, please bring them into class, and we'll answer them to the best of our ability. And have a good night.